There are several stages in the industrial production of methanol from methane. The first stage involves a gaseous equilibrium between the reactants, methane and steam, and some gaseous products. Figures 1 and 2 show what the percentage conversion of methane into gaseous products under different conditions at equilibrium. So we've got, first of all, percentage conversion at constant pressure but with increasing temperature. And what we can see, if we have a look at this, is that yield increases with temperature, but at a certain point it doesn't increase anymore. And then with the pressure increasing, yield decreases and then kind of tapers off as well. Okay, so we've got these two graphs and they're showing us what we should do to the temperature and what we should do to the pressure, and we're being asked to deduce the optimum conditions. And it doesn't mean specifically give a value for the temperature or pressure, although we could look at the graph and sort of say where the graph would say would be the best. But we don't have to know the answers. We're trying to explain what the graph shows us and what deductions we can make. So the first thing is we can say as temperature increases, yield, so that's the percentage conversion is giving us the yield increases until, and if we have a look, it's probably around about 800 until around 820 when yield no longer goes up. Now if we look at the other graph, we can see that as pressure increases, yield decreases, although again kind of levels off around 4,000. So above 4,000 kilopascals, yield remains fairly constant. That's just really what the graphs are showing us. So what would be our optimum temperature? So looking at that graph, we want a fairly high temperature, but probably below 800 degrees C. So fairly high temperature required, just below 800 degrees C. This gives optimum yield from the graph. But high temperatures are expensive as there are high energy costs. But they do give good rate because many more particles will have energy greater than or equal to the activation energy. So let's have a look at the pressure. It looks like we want a low pressure. Low pressure gives the best yield, but too low and the rate will be very slow, So a compromise may be needed. And if we go back to the graph, maybe we want somewhere between 1,000 and 2,000 kilopascals. In the second part of this question, we're doing something completely different. So we're now on to using values to calculate an equilibrium constant it wants us, first of all, to find out the amounts in the equilibrium mixture. So however you like to set these out, I'm going to set these out like a little bit of a RICE calculation. Remember that when we say RICE, we stand for ratio initial change equilibrium. So we're starting off with 20.1 moles of carbon monoxide and 24.2 moles of hydrogen and no methanol. And it says at equilibrium the mixture contained 2.16 moles of methanol. And I've just noticed that I've put my initial bit in the ratio, so let's just move those down. They shouldn't be there, should they? They should be in the initial amounts. The ratio should be there, and the ratio is 1 to 2 to 1. We can calculate one change, it going up by 2.16. Then what we need to remember is that the ratio line and the change line are in the same proportions. So if something has a 1 in the ratio, then in this line it is a 2.16 we can see. So this would be minus 2.16. So we can calculate that, 20.1 minus 2.16, and that's coming out as 17.94. And then here, because the ratio is a 2, we were going to minus 2 lots of 2.16. So we're going to do 24.2 minus 2 lots of 2.16. And we're going to find out that that's 19.88. So they gave all their numbers to 3 significant figures. You could give them as they are here, or you could round to 3 significant figures. Either would be acceptable. So the question then continues on the next page. It's a different mixture. This is just in case you've got those numbers wrong. Remembering the equation was carbon monoxide and hydrogen in equilibrium with methanol, which we can get from previously. And we're being asked to calculate a value for the equilibrium constant Kp. Now, Kp is the partial pressure of the products. Remember that these mustn't have square brackets. We round brackets over the partial pressure of the reactants. And it's the hydrogen squared because there's 2 moles of hydrogen. So this is one thing we needed. And then it's given us the equilibrium amounts. What we'll need to do is add up the total moles, because to use these partial pressures we need mole fractions. So total moles, 2.76 plus 4.51 plus 0.36. The total moles is 7.63. Then we're going to work out the partial pressures of each thing. So we'll start with the first one, carbon monoxide. 2.76 of the 7.63, and that's out of the 630 kilopascals total pressure, so 228. We'll repeat that method for the other two. 4.51 over 7.63 times 630. Do that on your calculator. 372. And then last one, partial pressure of methanol. So that was the 0.36 over 7.63 times 630. That's a smaller amount, 29.7. We can go back up and put them into this expression. 29.7 divided by 228 times 372 squared. And if you type that onto your calculator, you will get 9.41 times 10 to the minus 7. And we've used values that are all in kilopascals. All these pressures were in kilopascals. And we've had kilopascals on the top divided by a kilopascals and a kilopascals squared. So in total we've had kilopascals to the minus 2.